So Venn diagrams are useful to kind of help visualize sets and their properties. And, you know, I think we're all kind of familiar with what a basic Venn diagram looks like, right? So when you make a Venn diagram, you want to allow for all possible intersections. You know, I mean, unless you happen to know some specific information about your situation. So here we have a Venn diagram for one set. You'll notice that there are two regions here, right? If I have a single set A inside its universal set, when I draw the Venn diagram, it partitions the universe into two regions, what's in A and what's out of A. Once we move on to two sets, we end up with four regions. Right, because we're allowing for intersections. I want to allow for the possibility that an element could be in A but not in B. I want to allow for the possibility that an element could be in B but not in A. And maybe I could have some elements in both, and maybe I could have some elements in neither. If we move out to three sets, you know, we have to draw it, again, allowing for all possible intersections. So we have to make sure we kind of draw it in this way because of all these different possible intersections. You know, I want to allow for the possibility that something could be in A and B but not C, right? So that's this region right here. And we have, I think, if you count them up, 8 regions. Let's try 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Oops. We'll represent different sets by shading the regions that are represented by that set. So real quick here, some quick examples. We want to draw a Venn diagram and shade the appropriate region. So we have these three different sets. We have A intersect B, we've got A union B, we've got A set minus B. I'll notice in all three of these, we just need to allow for two sets, A and B. So my basic starting point will be the same, right? There's my A and B. A intersect B is just the sort of football overlap region, so we shade that in. A union B. What should we shade to represent the region or the set A union B? What's that? Yeah, well, everything in the circles, right? And one thing I've sort of left out, and usually it's not, some people write it and some people don't, but the understanding is that the rectangle box here is like, that's the universal set, right? So we understand all of these sets to be existing in their common universe. And then A set minus B. What region should we shade?
Just the outside portions.
What do you mean by the outside portions?
We should A and B circle.
I'm going to ask you to turn on your microphone. Thank you.
Okay, we should the A and B portion, just not the one in the middle that like intersects.
Okay. So you're saying this and this?
Yes.
You're half right. So we don't want the symmetric difference. We want just A set minus B. So that means everything in A that's not in B. In fact, it's just this crescent. What you're describing is the symmetric difference. So if we do one extra one, we use a little triangle. And that's this, what you described. Let's try another couple examples. Here we have some sets that involve three distinct sets, A, B, and C. And we want to, in the first one in part A, shade the region that represents the set A intersect B intersect C. So what's that region? Yeah, like just the middle, the very middle portion, right? It's just this part here. And in part B, we want to shade the region that represents, or that is represented by the set A union B, set minus C. So sometimes, you know, like this involves a couple of operations. So sometimes I might go at it piecewise. So maybe I'll start and I'll say, well, A union B. Well, that's the A and the B circles all together. So I'm just going to start with that. I know I might have to make some changes. Right, and then it says set minus C. So I want to throw out anything that's in C. So I'm just going to kind of erase the markings I made that included, you know, that overlapped with the C region. So it's basically that region right there. Venn diagrams can be useful to help illustrate when two sets are equal. It's not generally considered like a formal proof, but if I were writing, and we will do this in a little bit, if I were writing a proof to show that two sets, like a formal proof to show that two sets are equal, I might start by just convincing myself by drawing a Venn diagram. It gives me kind of a context, a jumping off point. Because it's kind of hard to prove something when you're not even sure that it's true yet, right? So we're going to use a Venn diagram to illustrate the fact that the complement of A union B is equal to the complement of A intersect the complement of B. So this says if I would look at everything outside the union, that'll give me the same elements if I take everything outside of A and intersect it with everything outside of B. So let's start with the complement of A union B. What should I shade? What region should I shade to represent the set complement of A union B?
We leave the circles and then shade everything else.
Yeah, we'll leave the circles empty, but shade everything outside. So that's this right here. Everything outside the union. So now that we've got that region, let's start a fresh Venn diagram to represent not A intersect not B. Now I might do this in a couple of phases, but I'm going to start. When you're looking for the intersection, what you're really looking for is an overlap of regions, right? You have to be in both at the same time. So I'm going to shade A complement separately. I'll do that first, and then I'll shade B complement, and then one could see where they overlap. So let's say here's A complement. Everything outside the A circle is there. And then I'm going to shade everything outside the B circle. And so I'm going to just draw one more Venn diagram to kind of clean this up a bit. Because if I'm looking for the intersection, I want to include everything that was shaded twice. Right? So any of the regions that I only shaded with just blue or just green, I don't want to include those. I'm only going to include, if I want the overlap, if I want the intersection, is the stuff that was shaded both blue and green. And the stuff that was shaded twice is all this stuff on the very outside. So again, it's not, a formal proof, but it certainly is illustrative and at least gets me to the point where I could say, oh yeah, that makes sense that these are the same, set. Questions so far? Okay. Well then, let's go over some properties of sets. So we start off with the idempotent laws, and that just says, and we're going to be able to fill these in ourselves for the most part. If I take a set A and I intersect it with itself, what should I get? Yeah, that's all the elements that are in both A and A. Clearly that's going to be the set A. How about if I union a set with itself? A, yep. If I start with all the elements in A, and then I add to that all the elements that are in A, I'm going to end up precisely with all the elements that are in A. The double complement law, what do you think the complement of a complement is?
Itself?
Yeah, it's just A again, right? So like the complement is kind of like a binary like on-off switch, right? It's like a negation or a not gate or something like that. All right, so next we come to De Morgan's laws, and one of these is the one we just sort of illustrated on the previous page. De Morgan's laws tell us that if I got a couple of sets, so we'll look at the top one here, the complement of A union B. This says I can sort of almost distribute the complement, but I have to flip the intersect, or I have to flip the sign between union and intersection. So this ends up being, and we saw this is what we just drew on the previous page, A complement intersect B complement. And it also works the other direction too. So what do you think we'll get if we take the complement of A intersect B?
A intersect union, B intersect.
A intersect, yeah, union, B intersect, right? So we can almost distribute that complement, but you got to flip that operation. And that wouldn't be hard to convince yourself of that with a Venn diagram as well. Commutative properties. What does commutative mean? Wait, what does it mean to commute?
To travel.
To travel, yeah. We can move things around. So commutative properties in mathematics mean that the order doesn't matter. I could write this in a different order. A intersect B is the same as B intersect A. Likewise, A union B is the same as B union A. Now the associative properties, these are the ones that tell us grouping doesn't matter. So in the top line, we're looking at A intersect B intersect C. But basically, the associative property tells us, look, if we're looking at take the intersection of all three sets, A intersect B intersect C, I can either choose to do the B intersect C first, find that, and then intersect that with A, or I could choose to find A intersect B first and then intersect that with C. Notice that the relative order in which I wrote the sets doesn't change. All that matters is the grouping, like right, what I did first. The operations is the same, right? So it's intersect, intersect, intersect all the way through. We get that same property with the union. So we get A union with B union C. That should be the same as A union B first and then union with C. The distributive properties are pretty much what they sound like. And that means the same thing that we meant when we, in regular old algebra and arithmetic, when we say that multiplication distributes over addition. This means the same thing. So the intersection distributes over the union. What do you think it should look like on the other side of that equal sign?
A intersection B.
A intersection B. Is your microphone on?
Oh, okay. A intersection B.
Yep.
Union.
Mm-hmm.
And B intersection. Sorry, A intersection C.
Yeah, A intersect C. Yeah, good. So the intersection distributes over the union. We also get the union distributing over the intersection. Each operation distributes over the other. And that is different from our experience with regular arithmetic, right? I mean, we know that multiplication distributes over addition in the integers, but addition does not distribute over multiplication in the integers. With sets, it distributes, each operation distributes over the other. So if union distributes over the intersection, what will this look like?
Same with this change of sign.
Yep, so what do we get? Turn on your microphone.
A union B.
A union B.
Intersection.
Mm-hmm.
A union C.
Yeah. Now we have some identities, identity properties. The empty set is the identity for union, for the union operation. And what I mean by that is, if you think about arithmetic with the integers, we would say that 0 is the identity for addition. Because if I add 0 to anything, I won't change it. Likewise, 1 is the identity for multiplication, because if we multiply anything by 1, we don't change what it is. So if the empty set is the identity for the union, and even without this spiel about what identity element means, I think you could all tell me what I should get if I take A and I union it with the empty set. We get A, right? I start with everything in A, and then I add to it nothing. I'm going to get A. What about if I intersect a set A with the universe? So I want all the stuff that's in both A and the universe.
A union universe.
It's not the union. I want this. It has to be in both at the same time to be in the intersection. Is there stuff in the universe that's not in A? No? So A stands for A stands for any arbitrary set, right, that exists in some universe, some universal set, right? So maybe think about this. For us, maybe our universe, the universal set, could be all persons on the Vermont Tech campus right now. Let's I'll narrow it down to Williston right now, and so everybody on the Williston campus, that's our universe, and A will be the set, just us in this room 214 right now. So if I take all the people in this room, and then I intersect it with everybody on campus, who is both on campus and in this room at the same time?
We get an A.
We just get A, right? It's just us, right? So everything in A automatically exists in its universe anyway, right? So if you're both in an arbitrary set and in the universe, you have to just be in that set. A Venn diagram illustration of this would look like this. So here's the universe. That's the rectangle. Here's our set A. I want stuff that's in A. It has to be in A, but it also has to be in the universe. The overlap has to be just A. Now, let's keep looking at that Venn diagram that we just drew. What happens, right? So A is the stuff shaded in black, right? What's A complement in that Venn diagram?
Universe.
Well, just the complement itself. Like what in the Venn diagram is the complement of A? We could just keep our mics on because there's not a lot of paper shuffling that happens. So say that again, Darren. Just the outside, right? A complement just means it's not an A. Okay. So that's A complement. Now what happens if I take A and I union it with A complement? What do we get? Feel free to pipe up out in Zoom.
The whole universe.
We get the whole universe, right? If I'm unioning it, right? I mean, I want to take everything that I have shaded. I've shaded the whole universe there. So when I union a set with its complement, we get the universal set. Right, Ralph?
Right.
Right.
Always good to have unions.
Yes. I'm a fan of unions. You might say I'm pro-union. What happens, let's look at the same Venn diagram, all right? So I got A shaded in black. I've got a complement shaded in green. What happens if I intersect them? Where's their overlap?
Set A.
So you're saying that the stuff in black is shaded in both black and green? What's that?
No, because it wouldn't be the complement in that case.
Right. So what elements are both in A and not in A at the same time?
Empty set.
Yeah, no, there's nothing that's going to be both in A or not in A at the same time. Remember, what makes a set well defined is that given an element, I can say definitively it's either in a set or not. You can't be both, right? That's a binary state. You're in the set or you're not. Now, some of these properties are kind of by definition, they're sort of axiomatic. Like, for example, the fact that the empty set is the identity for the union operation is really a definition of being a set. It's one of our axioms. But a lot of these we could prove. And so we're going to finish up today by writing kind of a formal proof that two sets are equal. Now, this is the one that we illustrated with a Venn diagram a couple of pages ago. Now I'm going to sort of outline, if I want to prove this in a rigorous way, right, beyond a shadow of a doubt, formally, we're going to sort of see how we do that. Now, we are proving that two sets are equal, and we mentioned, we saw this, we observed this in the last class, that if you want to prove that two sets are equal, what you're really doing is going to show that each set is contained in the other. So we're going to write two small proofs. So I'm going to start the proof. And especially in a proof where I know there's going to be kind of two phases, I like to let the reader know. Remember, we're trying to make sure that we are communicating our ideas clearly. So I'm going to let the reader know what my plan of action is. So we will show two things. One, we will show that the complement of A union B is contained in A complement intersect B complement. Oh, whoops. Hold on. I just got that backwards. This is the other De Morgan's property that we're going to be showing. Whoops. It's the complement of A intersect B equal to A complement union B complement. Okay. So that's one thing we're going to show, and then we're going to turn it around, and we're going to show that A complement union B complement is contained in the complement of A intersect B. So now let's get to work. Let's start with this first item. And to show that A intersect B complement is contained in A complement union B complement, we're going to start by saying let's let X be an element of A intersect B complement. What we're going to show is that this element X is also an element of A complement union B complement. The reason this works, the reason why this plan will establish this containment that we're after, is because I have assumed nothing about the element X other than it's in the complement of A intersect B. So it is an arbitrarily chosen element of X, which means if I can establish that X is in A complement union B complement, then that argument holds for every element I might find in the complement of A intersect B. So let's go, let's see where we get. If X is in this set, and I really just take kind of baby steps, when I'm writing this kind of proof. What I know is that X is in the complement of A intersect B. Well, what does it mean to be in the complement of something? It means you're not in the set. So I know that X is not an element of A intersect B. What has to be true in order to be an element of the intersection? What has to be the case? In order to end up in the intersection of two sets, what must be the case? Or maybe in this, another way to phrase it is, what does it mean to be in the intersection of two sets?
You're in both sets.
Yeah, you got to be in both at the same time. So if I know that X is not in the intersection, that means it's got to be either outside of A or outside of B, right? It just, I know it can't be in both. So I'm just going to write that out. Either X is not in A or X is not in B. So what I've done now is I've created two cases. One of these two things has to be true. It's either not an element of A or it's not an element of B. I'm going to take them one at a time. And either of those, regardless of which case it is, should lead me to the desired conclusion I want over here, that it's in the union of the complements. So if X is not in A, if it's not in A, where is it?
B.
Nope, not necessarily. What does it mean to not be in a set? We have a notation for this and a word for it. Let's keep our eyes on the prize. Where is it? We want to establish that X is in the union of A complement and B complement. I'm going to scroll up to the previous page to this nice Venn diagram. So think about this universe here. Here we're only thinking about one set, A, right? Either you're in A or you're not. And if you're not in A, if you're in the green region, what did we call that?
Universal.
No, the universe is the whole thing, the whole box. What's the part that's just green outside the circle?
A intersect.
No, what?
The complement.
Yeah, the complement, or A naught. Yeah. So that's what I mean when I say I'm really taking baby steps here. Like, I'm just going by definition. What does it mean to not be in a set? It means you have to be in the the complement. So we know that if this is the case, right, if X is not in A, then X is in A complement. And so if you're in A complement, you're certainly in the union of A complement and anything. And in particular, you're in the union of A complement and B complement. Right, to be in the union, you only need to be in one of them. So once I've established it's in one of these, then we're done. So we've handled this case, the X not in A case. Now we'll just repeat this for the other case. If X is not in B, then where is it? What? B naught, or B complement, yeah. And if you're in B complement, you're definitely going to be in the union of B complement with any other set. So for sure we could say X is in A complement union B complement. So this part right here, at this point, we can say definitively that we have established containment in one direction. We know that the complement of A intersect B is contained in A complement union B complement. Now, when you're writing just a containment proof, like there's some exercises and problems you might do where you're just trying to show containment, and so there really is just one direction to go in. When you're writing a proof that two sets are equal, you really got to make sure you cover both directions. it's really easy to get to a point where you've reached a conclusion and think that you're done and then leave the problem half done. And that's one reason why in the very beginning, I say I do this to outline for the reader what my plan is, but it's also for me to remember what my plan is so I can tell when I'm done. So we've done that first step. Now let's move on to the other containment. So to show that A complement union B complement is contained in the complement of A intersect B. Our plan, really we're going to attack this in the same way. What we do, and this is a basic strategy for a containment proof, is you let, you take an arbitrary element, so we let X be an element of, this set on the left, and then argue that it must also live in the set on the right. All right, so we know that X is in A complement union B complement. That's our supposition. So since X is here, A complement union B complement. Now I want to just take a small step. What is a small kind of close logical conclusion to draw? I'm in the union of these two things, A complement and B complement. What does it mean to be in the union? What's that? Yeah, so when you think about Venn diagrams, you could say I'm shading everything. But when you think about necessary and sufficient conditions to be in the union, if we're shading everything, in order to be in the shaded region, that means you only have to be in one of the two sets. I mean, you could be in both, but if you're just in A complement, then you're in this union, right? If you're just in B complement, then you're in this union. Or if you're in both, you're in the union too. So our logical conclusion, what gives us a couple of cases to go from, is that we could say that either X is in A complement or X is in B complement. Remember that a union is equivalent to the word or. So one of these are true. We've now established two cases. And just like before, if we take these cases one at a time, then I could take the first case, X in A complement, and then I want to try to argue from that it's going to be in our target set, the complement of A intersect B. So let's do that. If X is in A complement, what does it mean to be in A complement? What's that? Of what? I mean, you're certainly in the union of A complement with anything else. But we started with X being in that union. So what is it about being in the complement of a set? Like, what does it mean to be in the complement of a set?
To be outside of that?
To be outside of it. So we know X is not in A. Now, if you're not in A, the next sort of step I would take here, because again, I'm keeping my eye on the ball. I'm trying to show that X is in the complement of the intersection of A and B. Meaning, I want to make sure I can establish that X is not in the intersection. Well, I'm pretty much there. If X is not in A, you could not possibly be in the intersection of A and B. Right? To be in the intersection, you have to be in both sets. So if you're outside just one of those sets, that ruins your chances of being in the intersection. So X is not in A, which means X is not in the intersection. And if you're not in the intersection, if you're not in something, then you are in its complement. So X is in the complement of A intersect B. So that was one case. Now we can construct a really similar argument if X is in B complement. Right? It'll go pretty much the same way. If X is in B complement, then X is not in B. And if you're not in B, you can't be in the intersection of B and anything, right? So certainly you're not going to be in the intersection of A and B. And so now we've shown, since we covered both of our cases here, this has established the containment going the other way. So A complement union B complement is contained in A intersect B complement. And then, you know, if we're writing a proof, what you want to do is kind of tidy it up at the end. We now have sort of these two distinct arguments that we've made, and we want to let the reader know, look, we have accomplished our goal, and, hold on, I'm going to sneeze. Excuse me. And we want to let them know, we want to actually write down a clearly worded conclusion. So, maybe we have shown, or we can conclude, whatever whatever words you like to use. That A intersect B complement is equal to A complement union B complement. Now, I've written this entirely kind of with words in English. I mean, obviously, you know, we put in symbols there because I'm not going to write is an element of or is not an element of. I'm not going to write those out in words. We have nice symbols for that. And so there tends to be a mix of using mathematical symbols and English because we are, in fact, writing arguments. This isn't the only way it could be structured or written out. For example, I've kind of left out let's see, this symbol right here means implies. So if I look at, if I take this statement here, I could also write that same statement with this. X in A complement implies X not in A, which implies X not in A intersect B, which implies X is in A intersect B complement. That is just as well communicated. That's okay to do. So you might see a mix, you know, if you look at other resources, you might see ones written out more wordy, you might see ones written out kind of more concisely, you know, using a little bit more mathematical symbols to cut out, you know, verbiage, but they mean the same thing and they're equally acceptable in mathematical writing. The important part of this writing is that we are clear, that we don't leave any kind of holes, that we don't make assumptions we're not allowed to make, and that, you know, what I tell people when we're, you know, learning to write proofs and stuff and making sure that our arguments are clearly communicated, I say imagine that maybe a classmate isn't sure how to do a problem, right? you want to make sure that what you write would be easily understood by a classmate, somebody with a similar background, maybe who's learning the same stuff, so you could convince other people. The whole point of writing a proof is to convince somebody else that you're right. They could recreate your argument, and it would be conclusive. Are there questions on that proof? So if we have a set with some elements, first of all, an operator is unary if it acts on one element to produce another element. We say an operator is binary if it acts on two elements to produce another element in the set. And a Boolean algebra is a set with some elements and a couple of operations that behave in particular ways. So our Boolean algebra has to have some special elements that we call 0 and 1. They have to have some binary operations, which I'm just writing as plus and times, but don't think of it as like addition and multiplication of integers. We're just sort of using these as sort of these abstract kind of operations. And then a unary operator, which is like the complement. And what makes it a Boolean algebra is that the set with these operations behave according to these laws. These items A through E, we call these the axioms of a Boolean algebra. Those are the things we assume true. So when we prove some stuff about Boolean algebras, we do as much as we can by referring only to the axioms, so that we don't have to assume any new information. So commutative, we've already seen this when we were working with sets. The two operations, plus and times, are commutative. That means that x plus y is equal to y plus x, and x times y is equal to y times x. These operations are also associative. Remember, that's the one where grouping doesn't matter. We keep the relative order of the elements the same, but the grouping doesn't matter. And so that looks like x plus parentheses y plus z equals parentheses x plus y plus z, and then the same relation if we write this with multiplication. We have distributive laws. Each operation distributes over the other. Now, one of the ways in which we see this happen is that times distributes over plus, and when we write this out, this feels very normal, right? This feels very familiar because times distributes over plus in regular old algebra. But in a Boolean algebra, plus also distributes over times. So we could write that as x plus the product y times z, and if plus distributes over times, that means that this will give us the same thing as x plus y in parentheses times, in parentheses, x plus z. And that is generally not true with arithmetic, like what I might call plain old algebra. We have some identity laws. So 1 is the identity for multiplication. So that means that if I take anything and I multiply it by 1, I just get itself. That feels normal. And 0 is the identity for plus, so if I take anything and I add 0, I get the same element. Again, that feels normal. And we have, so far all of these operations that we've been using, we've just been focusing on plus and times for these axioms. Now we're going to, our last axiom is about what the complement does. The complement laws say that if I combine any element, if I add it to its complement, I get 1. Always. And if I multiply something by its complement, I get 0. Always. That is not very similar. That's not our experience with regular old algebra, but it very much is our experience when we think about, if we contextualize this in thinking about sets and set theory, like this complement law, the first one, this is the same thing as saying that if I take some set and union it with its complement, we get the universal set. Like 1 is like the universal set, 0 is like our empty set, and so like this other complement law, we could rewrite as I take a set and if I intersect it with its complement, that's empty, right? They have no elements in common. A couple of remarks. 0, we call it 0, no surprise there. Sometimes, not very often, but depending, if you look at other resources, they might refer to 1 as unity. And with the times symbol, it's just like in regular old algebra. Sometimes we omit it. So if you just see xy, it means x times y. So some theorems. Now again, so in the definition, those are axioms. Those are things we assume true. That is what defines a Boolean algebra. And everything else can be proven. We're going to prove some things, but not all of them. So first of all, we get the idempotent laws. These are the ones, let's see, if I take a if I take an element and I add it to itself, we just get the same element back. That's that equation just looks weird because, right, we're used to that being equal to 2x, but there, that we have no basis for that in a Boolean algebra. It makes much more sense when you think about it with sets, which, if you think about this with sets, we would write that as you take a set and you union it with itself, and you should just get the same set, right? You don't add anything new. If I take an element and I multiply it by itself, we also just get the same element, which again, that looks weird from our history of understanding algebra, but it's very similar. I mean, it makes much more sense if we think about this particular context. If we write it, what it means in terms of sets, it says if you intersect a set with itself, you just get the same set. The null laws. So one of these laws says if I take any element and I add 1 to it. Now, before I tell you what it is, maybe see if you can guess what you think the results should be, and it might help to think of this in terms of like x plus 1. What would that look like if I'm thinking about sets? So instead of an arbitrary element x, we might say we have an arbitrary set A. What operation is plus with sets? Guesses are fine.
Union?
That's a union. And what about 1? What element is 1 with sets?
It's the universe, right?
It's the universe. Okay, so what do I get if I take a set and I union it with the universe? So I start with a set, and then I add everything. What am I going to end up with? Yeah, you're going to get everything, right? We're going to get the universe. So now let's bring that back to the other equation. X plus 1 equals what? 1, yeah. The other null law, you probably already observed all of these come in pairs. So the other null law talks about what do we get if I multiply something by 0? So the operation or statement x times 0, if we write that in terms of sets, what does that look like?
That's going to be an empty set, right?
It's going to be the empty set. And well, in Boolean algebra, we'd say it's going to be 0. And when we write this equation with sets, it looks like if you take a set and intersect it with the empty set, you get the empty set. Now our last pair are the absorption laws. These ones are not entirely obvious, but again, I think we'll be able to understand it better when we think about sets. So the first absorption law goes like this. We have x plus x times y. That'll always give you x for any two elements, right? So here in all of these, right, x and y or whatever, they're always arbitrarily chosen elements. The other operation, or the other equation, looks like x times x plus y equals x. Thinking about what this looks like, I'll do the top one with sets. If I take a set A, and I union it with the set intersection of A intersect B. This should give us that same set A right back. And if we maybe think about making a Venn diagram here. So let's think about order of operations, right? This says start with A intersect B, right? And then I'm going to union that. I'm going to add elements. I'm going to add everything in A. So I'm going to just get the set A. Similarly, this last one says if I take a set A and I intersect it with A union B, we just get A. And that kind of makes sense. You start with the whole union, like the MasterCard logo, but then I want to, of that, only take the stuff that's in A. So I'm just going to get A. That's what this says. So we're going to prove some of these. And we're going to prove them using the axioms from the previous page. You know how, like, all of these laws, the axioms also, but in these laws, they come in pairs. So if you've been able to write a proof for one statement in a pair of laws, then you can always create the argument for the other one, the proof for the other one, basically just by flipping zeros and ones and pluses and times, interchanging them. You can recreate the argument using exactly the same axioms. So we're going to prove the idempotent laws first. So we're going to prove that x plus x equals x. And we're basically just going to do this. There won't be a whole lot of writing sentences. It's just going to be a really kind of efficient proof is just, you know, a long string of equal signs, which we can do just by using these axioms. So I'm going to start with the set x, or the element x. Now, one of our axioms says that any element plus 0 is equal to itself, like 0 is the identity. So I'm going to just write this as x plus 0, and that's a common strategy. If you're writing a proof with Boolean algebra, try to find a way to involve one of the identity elements, and then you can use one of those complement laws from the axioms to kind of rewrite 0 or 1 in some convenient way. So our reason here is this is the identity law. And I'm going to rewrite 0. 0 is the same as I take any element and multiply it by its complement. Now, I could take any element, which means I could have chosen to say y times y prime if I want, or z times z prime, but that would kind of be silly. We want our whole statement that we're trying to prove only involves one element, so I'm going to just stick with that. So this is the complement law. Now, you'll notice right here what we're looking at is I have x plus a product. So we're going to use the distributive property. It's the one we're not really used to being true, but does hold for Boolean algebra, plus does distribute over times. That means we can write this as x plus x times x plus x complement. And, you know, as I'm doing this, I'm always kind of keeping my eye on the ball. I started with x equals, and I know that what I want to do is be able to show that it's the same thing as x plus x. So I'm pretty excited that I got that x plus x there. So what can we do with this? What is x plus x complement?
That's a 1, right?
That's a 1, right? That's with the complement law on the previous page. So this is x plus x times 1. And one more axiom to use. What do I get if I multiply anything by 1? It's the one at the bottom.
You just get itself.
Yeah, just get itself. So this is x plus x. You know, one of the things I enjoy about Boolean algebra is, you know, I ask the question, like, what do you get if you multiply something by 1? And of course, in any other math class, it would just be automatic. We say 1, and then we have to stop and be like, wait, is that still true in a Boolean algebra? It is. So we started with, here's, you know, the basic structure of this proof. We started with x equals. We maintained equality all the way down, and we ended up with x plus x. So, you know, their powers combined here. Is that x is equal to x plus x. And that last one, I should write that was the identity law. So notice the order that we used here. In the next example, we're going to prove a different fact. We're going to prove that x plus 1 is equal to 1. That is the null law from above. And before we do that, though, what I just want to point out is that we proved that x plus x is equal to x. You could prove, like if you were setting out to prove that x times x equals x, you could do it by using precisely all the same axioms in the same order. You would just use the other version. So if I were, because this statement here, we call it the dual of this one, right? You get that statement simply by transposing plus and times, transposing ones and zeros. So if you were to prove this, the first thing I would do is rewrite x as x instead of x plus 0, x times 1. And then I'd rewrite 1 as x plus x complement, and then use the distributive property for multiplication over addition. So you can really construct the same argument when you're proving a dual. Let's do another. Let's prove that x plus 1 is equal to 1. And again, I'm going to start by involving the identity again. So I've got x plus 1. I'm going to write this as x plus 1 times 1, and that's an identity law. I'm going to rewrite this element 1 on the end using the complement law. So this is x plus 1 times, how can I rewrite 1?
X plus x is complement.
Mm-hmm. So that's the complement law. And at this point, what we could do is use the distributive law in reverse, right? So I'm going to scroll back to the previous page for a moment. So we write these. We think about, multiplication distributes over addition, or addition distributes over multiplication. But all of these equations work in both directions. So what we have in our, where we've left off right here is I have a product, x plus 1 and x plus x complement. So I'm basically looking at something that looks like this. So I can just use the distributive property in the reverse order and see this as something I would have gotten had I distributed addition over times. And that gives us x plus parentheses and then 1 times x complement. And of course 1 times x complement is x complement. Let me catch up with my reasons here. This is the distributive law. And then identity law. And as we've already observed, if I take an element and add it to its complement, we get 1. So again, we've started with x plus 1. We maintained equality throughout, and we get 1 at the end. How's that?
Can you explain the transition to the distributive?
Oh yeah, yep. So actually, I'll show it in the other direction. So we went from here to here, right? So what I'm going to do first is I'm going to start there. Because addition distributes over multiplication in a Boolean algebra, we could rewrite this as x plus 1, and then we bring down the times, and then x plus x complement. And so we're used to using the distributive property in that order more, but it's almost, it's weird to use this word. It's sort of like we're factoring it out, even though it's not a factor in the usual sense that we think of it. Does that help?
I'm sure it will once I get a minute to stew on it.
Okay. So starting from the stuff I wrote in blue here on the right side, here we kind of distributed and we worked in that left to right, like in the way we wrote it out in the axiom. So basically what I did when I was writing this out was saying, once I got here, as I said, oh, that looks like the right side. That looks like what I get if I were to distribute addition over multiplication in a Boolean algebra, and just tried to reconstruct what that looked like. It takes definitely a little practice, just because some of these rules are so counterintuitive from everything we've been learning over the last 15, 20 years of learning mathematics and all of all time. Other questions? So the thing, just to specify, maybe to clarify just a little bit more, the thing that really made me see that I could see this as something as having been distributed is that I had a common term in both. It was x plus times an x plus. And that's what made me say, well, that means I could take that out and then reconstruct the product. Let's do some more. We're going to prove one of the absorption laws. So we've already had a chance to kind of think about this in terms of, could we have gone straight from the, looks like Darren is asking, could we have gone straight from the distributive law to the solution? Well, I think that I do think that there's a step here. Once you use the distributive law, then we're here. And we still need to demonstrate that that's equal to 1. Right? So really what we're trying to do is make sure that we can explain or justify each step using the axioms. So I don't know that we can go from here and saying directly that's going to be equal to 1. I mean, it doesn't take long to get there, for sure. But we should emphasize, we should state what axioms we use along the way, simply because some of them are counterintuitive, right? We're kind of getting used to what these new laws are in this new structure that we call a Boolean algebra. So let's prove one of these absorption laws. We're going to prove that x plus the product x times y is equal to x. So I start with one side. Usually, I often will start with the sort of the business side, like what seems like I might have more opportunities. And like before, I'm going to work in an identity element here. So that first x term, I'm going to write that as x times 1. Now at this point, I'm going to use that distributive property again and again in the reverse order. This one will feel more normal just because we're adding 2 products. So this will feel like regular algebra. I've got an x times and an x times, so we can kind of, for lack of a better word, factor out that x. And inside we have 1 plus y. Now, because we just took the time to prove this on the previous page, I'm going to cite the work we just finished. We know, we proved in example 114 that what do we get when we, what should we end up with the parentheses there? What is 1 plus y going to be equal to? It'll be 1, yeah. Right, this is the null law that we proved. And now, of course, if I multiply anything by 1, I get itself. That's the identity law. And again, so we start with one side of the equation we wanted to prove, and we've maintained equality throughout, and we ended up with x. So our conclusion